In this lesson, we're going to be finding all the rational zeros of a polynomial. So before we do that, we need to discuss something called the rational zero theorem. And basically all it says is if given a polynomial, that has integer coefficients, so they must be integers, then every rational zero has the following form, and that's going to be p over q, where p represents the factor of the constant term, a sub 0, that's going to be this guy, and q is the factor of the leading coefficient, so a sub n, which is going to be that guy, so provided that it's in descending order. So what this means in plain English is if we create this little ratio of the constant term over the leading coefficient and list out all the possible factors, then you're going to list out every rational zero. But with that being said, we're not all of those ratios not all those ratios are going to necessarily be rational zeros. They're all possibilities, and within those possibilities you're going to get all the rational ones. And then from there we can find the irrational and imaginary ones. So let's look at a problem. So in our example, we're going to find all the real zeros of this quartic function. Now note it says all real zeros. So that includes the rational as well as the irrational zeros. And unlike previous problems we've done, this one does not give us any factors or zeros to start off with. So we're going to have to find those on our own. And we're going to be using the theorem, the rational zero theorem, to help us. So let's get started. So the first thing I want to do is I want to simplify our problem here by checking for any GCF. And indeed there is a GCF of 3. So I can factor out a 3 out of everything here. So that's going to leave me with 3x to the 4th plus x cubed minus 10x squared plus 2x plus 4. Now what I want to do is I'm going to see if I can find all the possible rational zeros of what remains in the parentheses here. So we're going to find all the possible rational zeros in our next step, and that's going to be our ratio p over q, remembering that p is our constant term, all the factors of our constant term, over q, which is all the factors of our leading coefficient. So I'll start off with factors of 4. So the smallest factor that goes into 4 is going to be 1. And I can include both a positive and a negative 1 here, because a positive 1 times a positive 4 is 4, as well as a negative 1 times a negative 4 gives us positive 4. So I'm going to include plus or minus. So that's going to be our p, and then our q is going to be factors of 3. The smallest factor of 3 is going to be 1 as well. So we're left with plus or minus 1 over 1. Then I'm going to continue using the 1 and the 4 and look for a different factor of 3. In this case, the only other factor of 3 is going to be 3. So I have plus or minus 1 over 3. So since I have no more factors of 3, I'm going to start using the next factor of 4, which is going to be 2, and then start over with 1 for the factors of 3, plus or minus 2 over the other factor of 3, so we're left with plus or minus 2/3. And then finally 4 is the last factor of our constant, and then over 1, and then plus or minus 4 over 3. The next thing I want to do is I'm going to simplify and reduce. By simplifying and reducing, sometimes you'll find that there are going to be possible rational zeros that are repeated, and we can take those out, and we'll just make our numbers look nicer as we simplify them. So we have plus or minus 1, plus or minus 1/3, plus or minus 2, plus or minus 2/3, plus or minus 4, and plus or minus 4/3. So there were none that were repeated in this particular problem. So we're left with a total of, if you're accounting for both the plus and minus, we have a total of 12 possibilities as far as rational zeros. Okay. So, and mind you, these are the rational ones, not the irrational, and we need to find all the real zeros, which includes both. So now what do I do? Well, one of these, or more than one of these, are zeros for our polynomial up here. But how do we know which one? Well, we could just select one and test it out. So, for instance, I could try positive 2. And how could I tell if 2 is 0? Well, remember, if something divides into a polynomial evenly, if a factor divides into it evenly, then it's going to be a factor. If you don't have a remainder, it's a factor. And since we're doing just a single number, a single zero here, we can use synthetic division. So that'll make it easier. So I'll try positive 2. And set up my synthetic division. So 3, 1, negative 10, 2, and 4. So we'll bring down 3, and then 2 times 3 is 6. 6 and 1 is 7. 7 times 2 is 14. Negative 10 and 14 is 4. 2 times 4 is 8. And that's going to give me 10. And then 2 and 10 is 20. We add those together, it gives me 24, a remainder. So this is not a 0. 2 is not a 0, and we can cross that one out. But we just did 1 here, and there's a total of 12 in this particular problem. So that seems kind of daunting to just guess and check and test it. So let's take a different approach, or let's do something to make it easier, to make us a better educated guess. So we'll break out our calculator, and we'll graph it. And the graph here looks like this. And as I can see, there's looks to be a total of 4 zeros, as we would anticipate. Some of these are rational, some of these are irrational. And it seems to me that it looks like we might have a 0 at negative 2. There seems to be one that is somewhere between 1 and 0, so maybe one of the negative fractions. It looks like there's one at 1, and maybe something a little bit above 1. So that's going to rule out, like 4 or plus or minus 4, and a number of the other possibilities. I'm going to go with 1, and we'll see if that works. Let's go ahead and set this up. So we'll do 1, and then 3, 1, negative 10, 2, 4. Alright, so we'll bring down 3. 1 and 3 is 3. 3 and 1 is 4. 4 times 1 is 4. Negative 10 and 4 is negative 6. 1 and negative 6 is negative 6. 2 and negative 6 is negative 4. And negative 4 and 4 is 0. There's no remainder, so 1 is a rational 0. So we can factor out an x minus 1. we'll rewrite this as 3 times, so we just found x minus 1 as a factor, leaving us with 3x cubed plus 4x squared minus 6x minus 4. Awesome. When I look at what we have left, we now have a cubic function. Now, one of the things I would try doing is maybe factor by grouping, but I've already tried it with this one and it doesn't work. So what that means is we're going to have to try to find some more rational zeros and divide. So we're going to have to do the PQ thing again. So we'll have to do the P over Q, but this time we're going to be using just this cubic function. So factors of -4 and +3. So again, our constant and our leading coefficient. So we'll start off with the 1. It's our smallest factor. 4, and our smallest factor of 3 is also 1. And plus or minus. And it looks like we're going to have maybe a lot of the same factors here. So plus or minus 1/2, plus or minus, it's going to be 2 over 1, plus or minus 2/3, plus or minus 4 over 1, and plus or minus 4 over 3. So when we simplify those, it's going to be plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 2/3, plus or minus 4, and plus or minus 4/3. So then we could go to our calculator and enter in that cubic function and determine, what would be a good possibility. Now, I already went ahead and I did that, and one that looked good to me was -2. So I would pull that one from our cubic function from the graph, and we'll substitute, or we'll set up our synthetic division. So that's going to be 3, 4, -6, and -4. Okay, so bring down 3, -2 and 3 is -6. That's going to give us -2. That's going to give us +4, and -2, -2, and -2 is +4, and no remainder. So that's going to be our other real or rational zero, at least. And I'm going to rewrite my function with this new factor of x plus 2. So we'll have 3x minus 1, x plus 2 is our new factor, and then we're left with 3x squared minus 2x minus 2. Wow, okay, so surely we are close to being done, and we are. All we have left is to find the factors of this quadratic. And, well, we could try factoring it, but that won't work. So that's going to leave us either completing the square or, you guessed it, the quadratic formula. Yes. So here we go. I'm going to identify, so we're just doing this guy here. So A is equal to 3, B is equal to -2, and C is equal to -2. So X equals -B plus or minus the square root of b squared minus 4ac all over 2a. So therefore, we just start simplifying that. X equals 2 plus or minus the square root, and that comes out to be 28 all over 6. Then x equals, we can simplify 28 because we can pull out a 4, and the square root of 4 is 2. So we're left with 2 square root 7 all over 6. And we want to simplify this. We can factor a 2 out of everything, which will leave us with 1 plus or minus the square root of 7 over 3. And those are going to be our other remaining 2 zeros. And those ones are irrational. So we won't find those using the P and Q. This would be the only way we can find that. So therefore, we finally have all our zeros. So we'll make one last grand statement here. As x equals -2, +1, and then 1 plus the square root of 7 over 3, and 1 minus the square root of 7 over 3. And we have found all 4. And that would be our example for finding rational zeros of polynomial functions. Till next time, I'll see you on the flip side.